Hi everyone. So today we are working further into our quadratic equations. Yesterday we learned to convert general form of a quadratic to standard form so we could see the vertex. Today we're going to continue that and move into graphing. Also, we will talk about a couple of things that you should already know about, but we'll remind you about because it's been a while. So today we're graphing quadratic functions, and the essential question: how do I identify important points and information excuse me, from certain forms of quadratic equations that should say help, let me fix that up, help me to sketch an accurate graph. Okay, so let's start with the way we started yesterday. We talked yesterday about general form of the quadratic being f of x equals ax squared plus bx plus c. And the important information we can get from that when an equation is written in general form, the a term, if it's positive, tells us that our parabola will open up and that our vertex is a minimum. And if we have a negative a, that our parabola has a vertical flip and that our vertex will be a maximum. The other information so that is some behaviors or information about the graph. It also gives us this point right here. C is the y-intercept. And so we can see information from general form that helps us sketch our graph. Also from general form, we could find the zeros or the x-intercepts of the graph by using the quadratic formula or factoring if that is possible. We talked yesterday about converting from general form to standard form. Standard form of a quadratic also tells us a critical point and some information. It looks like this: f of x equals a times x minus h quantity squared plus k. And that a has the same information as the a from general form, but the other important information is that it gives us the most critical point, which would be the vertex at h. Okay. Also in standard form is also the transformational form. So basically, we could take the parent function and transform the parent function, pardon me, by taking the parent function y equals x squared and putting it through the transformation of doing your vertical a and then shifting it h and k and graphing your parabola. So we could say that the parent function can be, I wanted to write the word can be transformed using the information in standard form. So you get that critical point, your vertex, and then you could graph the whole thing if you know how to use your transformations. Okay, so that's important. Something else that I'd like to remind you about. So we know now that we can get the y-intercept from general form. We can get the general shape of the graph from your a term, and that happens in standard form or general, and we can get the vertex from standard. The other critical points that are typically necessary are to find the zeros or the roots. And so let's talk about those for a second. Zeros, also known as roots or x-intercepts. How do we find those? And what kind of zeros are there? So just a little refresher on some old information. There are 3 types of zeros. Okay, and so there are 3 types. And let's see, what else? I want to talk about the square root of b squared minus 4ac. that tells us some information about our x-intercepts or our roots. So I'd like to talk about the types of roots that the discriminant is what that's called, creates, and then what does the graph look like. So let's look at the different types. There are, you can get 2 real zeros, you can get 1 real zero, or you can get 2 imaginary zeros. And I'm not going to finish writing out imaginary. I think you've got that. Okay? And so those are the types. Now, in order to determine if we have 2 real, if we're looking at the discriminant, if we're using our quadratic formula here, the number underneath the radical, once we simplify it, will be a positive number. Okay, and what that will look like if we were to graph it, if a quadratic or a parabola has 2 real roots, it has 2 x-intercepts, 2 zeros, so the parabola will intersect the x-axis in 2 spots. And so that's what that would look like. All right, it'll have 1 real zero or x-intercept if what's underneath your square root after you simplify is a 0. And so if a parabola has 1 x-intercept or 1 0 or 1 root, that parabola will have a vertex that actually bounces off of the x-axis, and it'll have 1 real. Then if the zeros, there are always 2 imaginaries, they come in pairs. Okay, we'll have 2 imaginaries if what's underneath your square root is a negative value or a negative number. And if you have a parabola, a quadratic that has imaginary zeros, when they come in pairs, your parabola will float, and those points will be somewhere, but I won't ask you, of course, to graph them. So that's just a reminder about zeros. A couple ways you can find them. To find zeros, if you're working from general form, you can factor if it's factorable, or you can use the quadratic formula, which I will put right here. So x is equal to, remember, negative b plus or minus the square root of b squared minus 4ac all over 2a, where this value here determines the types of zeros that you have. Okay, if it's in general form, those are typically the most familiar and popular ways to find your zeros. And if you're finding your zero from standard form, I'm actually going to show you how to do that. Well, I'll just do this in standard form. To find your zeros, you just plug in 0 for f of x and solve for x. So that's what you would do for standard form. Okay, so let's take a look at this problem that I have provided for you. Let me extend my screen out a little bit. Hopefully that doesn't cause a problem. Maybe it'll let me do that, I'm not sure. It doesn't look like it will. Okay, well that's not a problem. We'll just bring it back. And I will zoom out a little bit. So let me just do that really quick. Well, it won't let me zoom out either, so we'll just make it work. So we're going to start with this first information, this first step, 4f of x equals negative 2x squared plus 4x plus 3. We're going to identify the useful information from that form before converting. So step 1, I'm going to take negative 2x squared plus 4x plus 3 equals f of x. And here's what we know. Our a equals negative 2. Therefore, our parabola opens down and it has a maximum as a vertex. And that our y-intercept is 3 because our c is 3. which is our y-intercept. Okay, so that means that I could go ahead and go to my graph, and I could graph the y-intercept of 3, and I already have a critical point on my graph. Okay, moving on, because we're just being efficient, let's convert this to standard form to identify and graph the vertex. This is what we learned to do yesterday. So we'll take negative 2x squared plus 4x, and we are going to subtract the 3, move the constant to the other side. So that will be f of x minus 3. Just get that out of the way. All right, next step is to factor out the a term. So we're going to factor a negative 2 out of x squared plus negative 2x squared plus 4x. So that'll leave us with x squared minus 2x equals f of x minus 3. And then we will complete the square here. So we will take our b term right here and we will cut it in half and square it. So half of negative 2 is negative 1. Negative 1 squared is 1. Now remember that we're not adding 1 to the right side. Left side, we are adding negative 2 times 1 to the left side, which means that we also have to add a negative 2 to the right side. Okay, to keep our equation balanced. Now let's factor our perfect square trinomial. So that'll be negative 2 times x minus 1 quantity squared. Remember, it's just the number of your b term cut in half. 1 times 1, negative 1 times negative 1 is 1, and negative 1 plus negative 1 is negative 2. So that satisfies the conditions for a perfect square trinomial. Equals f of x. We'll simplify the right side here. Equals negative 5. Or minus negative 5, pardon me. Now we'll add 5 to both to put it back in standard form. So we're going to put that back over there. So we get f of x is equal to negative 2 times quantity x minus 1 squared plus 5 with a vertex at 1, 5. And then I'll go run over here and sketch that. Okay, so let's take a look at if we did everything for step 2. We did what we needed in step 1. Yep, we converted it to standard form, identified, and graphed the vertex. We did that. All right, next it says graph the axis of symmetry and label it x equals whatever x equals. All right, so let's take a look at this. Axis of symmetry passes through the vertex, so we're going to drop in our vertical axis of symmetry here. And that is crossing the x-axis at x equals 1. And so if I come over here, I say, okay, so my axis of symmetry is coming from my vertex where x equals whatever the x in my vertex is. So there we have that. So that's done. All right, then the next question is a test question. So we definitely want to make sure that we can do this. It says identify the maximum or minimum value of y. Now we've already determined that our parabola opens down, so our y, our vertex is our maximum, right? And our maximum here, our f of x, is equal to 5. So here we have a maximum value. This is the highest value for f of x equals 5, and that is also coming from our vertex. Also, by the way, this is going to be a question that you will see on the test coming up. So when it asks you to identify the maximum or minimum value of y, go to the vertex to find that. Okay, now I do want to take a moment to step back. The reason that we put an axis of symmetry here is so that we can treat it like a mirror and reflect points across that axis of symmetry. And so I'm going to reflect the y-intercept. Now we have 3 really nice points on our parabola that are already sketched. All right, let's go to the next step. The next step, it says to find the zeros. And I'm going to erase a little bit of work. You have it already, so that we can do that. So 2 ways you can go about finding the zeros. You could use your quadratic formula or try to factor from general form. I'm not going to do that because you guys have done that many times in the past. Or you can use standard form and plug in 0 for y and solve for x. So that is what I'm going to do, just because it's not as common of a way to solve for zeros, and I would like you to practice it. So for step 5, and I didn't mean to have my red pen there. So step 5, we're going to find the zeros by taking our f of x and turning it into 0, and that is equal to -2 times quantity x minus 1 squared plus 5. And actually, I'm going to move the 0 to the other side. I don't like it over there. I like it over here. Okay, so we're going to just solve this for x. And I'm not going to simplify this equation by expanding and multiplying x minus 1 quantity squared times itself and putting it back in general form. That's such a waste of our time. X is already pretty isolated, so I'm just going to start moving these numbers that are not grouped with the x off, take the square root, and find our solution. So we'll subtract 5 from both sides, and we have -2 times quantity x minus 1 squared equals -5, and then continue to move numbers away by dividing by -2. And here's what we get. X minus 1 quantity squared equals 2.5. And now we will apply the square root property. So we'll square root x minus 1 quantity squared equals, don't forget that you are introducing the plus and minus square root of 2.5. And let's just be clear that that means that there is a positive number under our square root. Therefore, we will have 2 real zeros. So we will be graphing 2 x-intercepts. So we'll cancel that there, and we get x minus 1 is equal to plus or minus the square root of 2.5. And then we'll add 1 and slide it right up front. I'm going to do a little more erasing so we have a little room here. All right, so we get 2 solutions. X equals 1 plus the square root of 2.5 and 1 minus the square root of 2.5. And of course, that's not useful for graphing, but that is an acceptable response. So we'll get just an approximation with our calculators, and we'll go to 3 decimal places. So 1 plus the square root of 2.5 will be 2.581, and 1 minus will be -0.581. And so we'll go ahead and graph the zeros, or our x-intercepts. So x is just a little past 2.5, and negative x, our negative x-intercept is here. And so now we can sketch a nice graph, which is the last step in our process, and this is really difficult for me to do. You'll do a better job. Your hands are a little bit less shaky than mine. So we sketch the graph. Now here's something that I just want to point out that we could have done at step 2. We could have sketched the entire graph, because if you recall, I did tell you that when an equation is in standard form, we can just graph the parent function and then use the transformations, the a, the h, and the k, to actually graph the function. And so here's what I'd like to show you. I'll do that in a different color here. And so let's say I take the parent function of x squared. F of x equals x squared. So this would be your parent function, right? And so I'll just do a little sketch of the parent function. And then let's just take a look at what's happening here. I'll do a little description. So what's happening here is that we have a vertical, stretch and flip by multiplying our y's. So we're doing y times -2. And that would be, we could just go ahead and flip this and stretch it vertically. And then we would have, let's see if I can find another color here. I'll go with purple. And then we would horizontally, you were going here now, we're going to push the graph points right 1. And then vertically, we're going to push the graph up 5. Just working off our transformations of our A, our H, and our K. So first, I'm going to do the vertical stretch and flip. So we're going to take this 0, y equals 0 times -2, so it's still 0. y equals 1 on both of these times -2 is -2, so those points are going to flip and stretch down 2. And then, of course, these points here where y equals 4, we'd go times -2. That'll be down here somewhere at -8. So that's the stretch and flip vertically of that function. And so we could do that if we'd like. And then what I'm going to do now is grab my purple pen again and then just take all of the points on my flipped graph and push them right 1 and up 5. So right 1 up 5, there's my vertex. Right 1 up 5, there's the reflection of my y-intercept. Right 1 up 5. There we have it. These points right 1 up 5. And let's see, did I get that one right? Right 1 up 1, 2, 3, 4, 5, somewhere right here. And right 1 up 1, 2, 3, 4, 5, right there. And you can see that those points follow along that graph that we just created when we were graphing all of the points singly and not putting it through the transformation. Okay, so a lot of review there, and then some information that will help you maybe just refine what you know, help you be more aware of the critical information that you can get from each type of quadratic equation so that you can sketch graphs, and then you have all of these little checks, these things that you can check to make sure you're not making errors.